Welcome to Module 10 of Mechanics of Materials Part 1. Today's learning outcomes are to define and discuss material properties associated with that stress-strain diagram that we developed last module. And we're going to define something called Hooke's Law. So here is our normal stress-strain diagram for a ductile material, typical ductile material that we came up with last time. So with this stress-strain diagram, we can start to look at material properties. And the first property we're going to look at is what we'll call stiffness, and that's in this linear elastic region. We said that the slope of the line in this linear elastic region was E, or what we call Young's modulus, or modulus of elasticity, and it is used in what's called Hooke's Law, which is valid for the linear elastic region, where the stress is equal to Young's modulus times the strain. And Hooke's Law was named after British physicist Robert Hooke, but it was actually believed, the concept was believed to be developed first by Leonhard Euler. But the stiffness, the slope becomes greater and greater as the material is more and more stiff. And as it goes down, it would be less and less stiff. So as examples of material that would be less stiff going to more stiff, you might start off with something like rubber, okay, where you get a lot of strain for very little stress, so that's got low stiffness. Human bone or cartilage would be maybe a little bit higher stiffness, and then maybe concrete, and then you get into your metals like aluminum, and then copper and steel have a little bit more stiffness than aluminum, up to things like tungsten or graphene, and finally maybe a really stiff material as an example would be a diamond. Okay, let's look at some more material properties from the stress-strain diagram. The next one we'll talk about is strength, and that's the capacity for high stress, or the material where the material has its ultimate stress, or ultimate, what we also call ultimate strain. And the strong material would be something like multi-walled carbon nanotubes or something like that. A lot of ultimate stress that it can take. And so capacity for high stress or ultimate stress. Next, we talk about toughness, which is the capacity for energy absorption. And it can be shown that the energy absorption is the area under the stress-strain curve. So the more area we have under the stress-strain curve, the more energy can be absorbed. And an example of this might be like a guardrail, where you want it to deflect a lot, take a lot of stress, and take out the energy. Or maybe a barrier at a toll booth. Another property we talk about is resilience, and that's the capacity for deforming elastically, which is the area under this elastic region where it can continue, the material can continue to be bounced back to its original shape. That's the resiliency of the material. And then we talk about ductility. We talked about it quite a bit now. That's the capacity for high deformation or strain, and so that's when this stress-strain curve becomes very, very long, lots of strain for very little increase in stress. And ductility, a lot of metals are very ductile, things like steel, aluminum, copper, maybe lead, brass, bronze, those are all ductile materials. And then we call a brittle material one that has very low capacity for deformation or strain, and so as we go up, we get into this plastic region, it fractures a lot quicker than a ductile material would do. And some examples of that would be like concrete or glass or cast iron or ceramics. And so those are some typical material properties. Now what I'd like you to do is complete a worksheet to look at typical stress-strain diagrams for different materials and pick off values. And so here I have three typical materials. We have a standard structural steel alloy, we have a common aluminum alloy, and a magnesium alloy. And so for those different materials and those typical stress-strain curves, what I would like you to do is to answer these questions. And so go through, find the modulus of elasticity for the steel, ultimate strength, and go on all the way through. And then I've gone ahead and put the solution to this worksheet in the module handouts. And we'll see you next time.